Okay, we finally finished the gas law chapter, so we're ready to move on. Now, if you'll remember, back when we actually last saw each other, um, the plan was this chapter 5 was supposed to be the next chapter we were going to cover. It was still out of order, but that was the next thing we had in mind. But with the shutdown coming up, we skipped ahead and did chapter 14 on gas laws because I figured the math there would make it just easier to do that online than a more conceptual chapter. And I figured, man, by the time we're done with that, we'll be back to school and we can do chapter 5 together in class. Well, that didn't work out real well now, did it? So unfortunately, that means we got to go back and do chapter 5. And there's a couple other chapters on bonding after that I want to get through also. And these chapters are much more conceptual. So there's ideas and things you have to just understand through lecture. It's not the most ideal way to do it. I'd rather we were back in the classroom doing this, but we don't get our choice here. So let's take it slow and carefully and see how it goes. Now, once again, I'm going to complain about the way the chapter organizes this. Section 1 that we're going to start in today gives you just an overview of the whole thing, from what we learned way back in the beginning of the year of atoms, all the way through talking about the modern day quantum mechanical model of the atom. And they give you just a superficial overview of everything. And then they start filling in details later. I prefer to go through it more historically and show each step along the way as they figured out new things, but the book did it a different way. If we were doing this together in class, I would tear it apart and rearrange it and do it my own way, but I don't want to add to confusion here. You're on your own at home doing this for the most part, so I want to keep it as aligned to the book as I possibly can. So we'll do it their way, and I'll be sad about it, but we'll do it. Okay, so Section 1, the atomic model as we know it so far. They talk here about models in general. You do a plastic model of some guy skiing. A globe is a model of the Earth. We make models of the atom as well, although those models don't have to be physical things you can hold in your hand or even draw on paper. The most modern model we have is a very mathematical model. So much mathematical, in fact, that we can't deal with it because you need many, many years of calculus before you can even read the equations. So we're not going to do that. We're just going to get the concepts that come out of it. Now, we'll ignore that. Let's go back to the good old days. You'll recall we started out with Dalton coming up with a model of the atom. That was basically their little marbles, and that was it, right? And then we had the plum pudding thing, but we laughed at that. That didn't last real long. And finally, Ernest Rutherford came along and gave us a model of the atom that made sense and that we kind of have been using all along. There's a nucleus in the middle. In that nucleus is protons and neutrons. And then electrons are orbiting around that nucleus like planets around the sun. Often it's called the planetary model of the atom. So, if you let me come out of the PowerPoint for a moment, I can actually draw that, I suppose. You got your nucleus with a positive charge in the middle. And then here's an orbit, and there's the electron. It's so small I can't really draw the negative sign real well in there. The electron orbiting around the nucleus like it was a planet going around the sun. I can't find my cursor. Oh well. That model of the atom worked well, but it doesn't explain some things about the atom that it really needs to. And there are some flaws in it. Taking the electron and having it zip around like a planet. Remember, planets orbit the sun because of the gravitational force. And that works out well, or we wouldn't be here if it didn't. Electrons, though, they orbit the nucleus because of an electric force. The opposite charges of positive and negative attracting. Gravity is so weak at that down on this scale, it's irrelevant, and they ignore it even in the equations. So it's a different force holding the electron in orbit. Now, back in the day, all they knew was the two forces, gravity and electricity, use similar equations, so they figured the forces should work similarly even at this scale. But it turns out there are issues that arise that it won't work. Trying to put an electron in orbit around the nucleus, the electron would actually emit light of various frequencies, meaning colors, and eventually crash into the nucleus. So if Rutherford were right, the electron is like a planet orbiting around the nucleus, atoms wouldn't be stable for more than a fraction of a second. And obviously we know that's not true because we have atoms. So let me come back to the PowerPoint. And so Rutherford's model, nucleus with electrons orbiting like planets, was a very simple model, very straightforward model. It explained the whole scattering of alpha particles from gold foil, if you remember that experiment. It explained that quite well. And explained a few other simple things about atoms. But there's a lot of things it can't explain about atoms. Gold is a metal, and it's so incredibly unreactive that you can drop acid on it and it just laughs. It won't react with it for the most part. Sodium's a metal. It's so unstable, so reactive that if you put water on it, it blows up, or at least bursts into flames. Why are those two metals so different in their properties? One ridiculously reactive and unstable, the other incredibly stable. Rutherford's got nothing. It's got electrons orbiting the nucleus. Why do these electrons act differently from those? Not a clue. So Rutherford's model really can't explain why elements have different chemical properties from each other. So the model is limited. Do we throw it out? Not completely. We keep the ideas that work. Nucleus, electrons outside the nucleus. That's been shown quite well with the gold foil thing. But we have to adjust the theory and adapt it so that it works better and explains the properties of elements better. So the book points out a property that we call blackbody radiation. I'll talk a little more about that later. Again, I'd prefer to do this sequentially and talk about it now, but we'll do it their way. If you take an object, in this case they're taking, let's say, black iron, and heat it up, it eventually starts glowing dull red. And then you make it hotter, it starts glowing orange, and then yellow hot, and so on. Eventually you might get to white hot, blue hot, and so on. Notice as you heat the object up, you put more energy into it, the color that it glows changes, as well as the brightness that it glows is changing. That concept was well known to scientists. They called it blackbody radiation. And based on the theories of the day, it shouldn't have worked that way. It should have worked differently from what we see. And so Rutherford's model and other theoretical models they had at the time were flawed and didn't explain why the glowing worked the way it did. So the first attempt to fix that was a guy named Niels Bohr, who, interestingly enough, was one of Rutherford's students. Just like Rutherford proved his teacher Thomson wrong, Bohr comes along and turns the tables and proves Rutherford's theory's got to be wrong. So he basically took the planetary model, nucleus in the middle, electrons orbiting, and modified it in a way that was an attempt to fix the way light is absorbed and emitted by atoms, as we briefly saw a little with blackbody radiation. Another factor in that they don't tell you here, and we'll talk about again on our own, we would have done a lab on this if we had been at school, is that different elements, if you pass electricity through them, or if you just put them in a flame and vaporize them, they'll burn different colors. They'll glow different colors. Neon glows the characteristic reddish orange of neon lights. Sodium glows bright yellow. Copper glows green. So every element, if you see fireworks, you see a red firework, they're probably using strontium nitrate in there. Very romantic when you're out on dates watching fireworks, right? So each element has its own characteristic pattern of colors that it emits and absorbs. Why? Bohr's model was an attempt to explain that. He basically took the model and said, okay, you got a nucleus, you got electrons orbiting the nucleus, but the electrons can't orbit wherever they want. Okay? The electron can only orbit in certain specific circular paths around the nucleus. So he still kept orbits like planets. Oops, what did I do? Oh, ad block, great. He kept the orbits around the nucleus, but he changed it so that you can't just orbit anywhere you want. With Rutherford, he just assumed an electron could orbit anywhere it felt like orbiting. Give it a little energy, it can move to a higher orbit. Bohr realized that can't be the case. If it was, there'd be no patterns of colors like we're seeing. So Bohr's model is that the electrons orbit at specific energies, and each energy corresponds to a particular distance orbiting from the nucleus. They call those energy levels or energy states. A quantum is a unit of energy, the amount of energy to jump from one state to another. So sometimes they're called quantum states. Now, here's the picture I was looking for. This ladder is kind of an analogy for Bohr's model of the atom. If you look at it closely, the rungs get closer together as you go up, which makes it a terrible ladder, but it fits Bohr's model. The electrons can only be on the rungs of the ladder. And you can think of the size of the ladder as an energy graph. So this rung right down here is low energy. That rung has higher energy, higher yet, and so on. And notice the amounts of energy get closer together as you go up. So the electron can have an orbit equal to this energy right here, which would mean orbiting some distance from the nucleus. If you give it just the right amount of energy, it can jump up to this energy and orbit at a different distance from the nucleus. You give it a little more, it could jump up to that energy. Now, can you give it enough to jump from here to there? No, that's halfway between. There's no energy state there. The electron may not exist anywhere between orbits. So the electron can only exist at these specific energy states. It may not exist anywhere in between. So for neon, for example, that reddish-orange light might be a jump from here to there. What if I give it light that's the wrong color? Maybe it's infrared, lower energy than red. It would get it to here, which it can't be there, so it can't use it. What if I give it like green light, which is more energy? That would put it up here. Can't use it. It got to be the right amount of energy. Got to be just the right amount of energy to get from here to that rung up there. And for neon, that happens to be reddish-orange light. For sodium, it's yellowish light. For copper, it's greenish light that does it. So the spacing of the energy states determines where the electrons are going to orbit and determines ultimately what colors of light it's going to absorb or emit as it absorbs light energy or emits light energy, jumping from level to level. And that's Bohr model. The electrons jump from energy state to energy state as they gain or lose energy, and they do so by absorbing or emitting photons of light. They called that a quantum jump or a quantum leap, which, by the way, is scientists don't like that. Because how does the electron get from there to there? It's kind of just beaming up. So quantum jumps are weird things, but they happen apparently. So that's Bohr's model of the atom. Now, how does Bohr's model improve on it? Rutherford's model couldn't explain to us why specific colors of light. Why does sodium glow yellow? Why does copper glow green? Why does neon glow reddish orange? Rutherford says, I don't know. It just does. Bohr's model can explain those colors of light by calculating where exactly those rungs of the ladder are and finding it agrees with reality. Well, technically, Bohr's calculations only really worked for hydrogen atoms, and they failed when they applied to the other atoms. So that brings up Schrödinger and his quantum model of the atom. Erwin Schrödinger comes along and realizes Bohr's model is a good first step, but it still kind of fails. And so we get this quantum mechanical model of the atom that good old Erwin Schrödinger, that umlauted O, gave us. He came up with a very complex equation based on wave mechanics that allowed him to calculate better the energy states of the electrons, where the rungs of the ladder are. His theory got the calculations right. It got the lines in the spectrum exactly where they are, got the colors exactly where they should be. The cost, though, was he had to treat the electron as a wave. So now the electron's not some particle orbiting the nucleus or sitting on a ladder or rung or anything like that. It's some blurry wave function that I can't draw. It's just a mathematical concept. And that blurry wave function, what we call an electron cloud ultimately, when you calculate the energy states there, can tell you what colors of the spectrum the atom is going to absorb or emit. And so the model works extremely well and explains a lot of other things too that we're going to talk about, but at the cost of being mathematically very complex and very difficult to understand, and even worse, there's no picture of the atom I can draw anymore. Let's leave it at that for now, and tomorrow we'll finish section 1 and talk about some details of the Schrodinger equation. All right, talk to you later.